So in today's lecture, we will see one of the characterization techniques of nanomaterial or nanostructure, as you have seen in the previous lectures. This is also one of the characterization technique which is used to study the morphology of nanomaterial or nanostructures. Right. So earlier we have fabricated the nanomaterials in different process, and we have characterized it by using different characterization techniques like XRD, scanning electron microscopy, transmission electron microscopy, and atomic force microscopy. So in today's lecture, we will see how to characterize the nanomaterials by using magnetic force microscopy. So magnetic force microscopy is nothing but simply the MFM. Magnetic force microscopy is simply nothing but MFM, which is called magnetic force microscopy. This is somewhat analogous to atomic force microscopy that we have seen in our previous lectures, right? So the MFM is nothing but magnetic force microscopy, right? So magnetic force microscopy is based on the use of ferromagnetic tip as a local field sensor, right? So magnetic force microscopy is based on the use of ferromagnetic tip, right? So tip means we understand. So this is our material. So this is our cantilever, right? So where we have certain tip like this, where this particular tip is placed on a material, on a substrate, so that the cantilever frequently vibrates with the material, and due to this vibration, some amplitude, some frequency, some oscillations can be easily studied, right? So that's what MFM is based on the use of ferromagnetic tip as a local field sensor, right? Local field sensor. Magnetic interaction between the tip and the surface results in a force acting on the tip. Magnetic interaction between the tip and the surface results in a force acting on a tip, which can be detected from the deflection of the cantilever. Alternatively, the dynamic properties of the tip oscillation, that is amplitude, phase or frequency, can be studied, can be used. In this case, the observed signal is proportional to the derivative of the force. The signal is proportional to the derivative of the force, right? So here the tip that we have used is scanned several times or hundreds of nanometers about the sample, avoiding the contact. So magnetic field gradients exert a force on the tip's magnetic moment, and monitoring the tip or cantilever response gives a magnetic force image. To enhance the sensitivity of the magnetic tip, the most MFM instruments is oscillate the cantilever near its resonant frequency with some piezoelectric material. So for that, gradients in the magnetic force on the tip shift the resonant frequency of the cantilever, resonant force on the cantilever. Monitoring this shift or related changes in oscillations can be observed. So here the tip is scanned several tens or hundreds of nanometers above the sample, avoiding the contact. So magnetic field gradients exert a force on the tip's magnetic moment and monitor the tip or cantilever response, which gives us the magnetic force image, right? So to enhance the sensitivity, most MFM instruments oscillate the cantilever near its resonant frequency with some piezoelectric element, crystal. So gradients in the magnetic force on the tip shift the resonant frequency of the cantilever. Monitoring this shift or related changes in oscillations also can be observed. So monitoring this shift or related changes in oscillation, that means amplitude or phase, produce some magnetic force images. So the applications that are mainly concerned is a magnetic recording media. So that is what's on our application for magnetic force microscopy, right? Magnetic force microscopy has very important application in magnetic recording media, that is like MRAM materials. We call it as MRAM, magnetic random access memories. That is what we call it as MRAM. And not only that, MFM images are the experimental images that can be seen on a fabricated material, that can be seen on a fabricated nanostructure. So to simulate that particular magnetic nanostructure, right? To simulate that particular MFM image, people go for some simulations. Right? So such type of simulations are what we call it as micromagnetics. So this micromagnetic software called OOMF, Object Oriented Micromagnetic Software, which is an essential tool to simulate the characterized material by magnetic force microscopy. So that is what we call it as a micromagnetism. So magnetic recording media, micromagnetism, and is also used to study the domain wall dynamics, because when we talk about the domain wall dynamic, so in thin films, we observe some Neal walls. In thin films, when we fabricate a thin film on a substrate by a ferromagnetic material, the film so produced will become Neal walls. Neal walls will be produced in the thin films, whereas the domain walls will be produced in the bulk form of thin films. As in thin films, Neal walls will be observed, and in bulk films, the domain walls will be observed. So to frame the dynamics of the domain walls that are framed, people go for this type of image, magnetic force microscopic image. So we can see the domain wall motion, that is what dynamics can be framed, and also pinning. So pinning in the sense, what sort of pinning can be observed? Right? So as a result, some vortex states are framed. Right? So it is also used. This magnetic force microscopy can also be used to study the failure analysis in electric circuits, and also to study the superconducting current. So these are some of the applications where magnetic force microscopy encourages. So this is what the image of magnetic force microscopy. So we have a cantilever here. So this cantilever is placed on a substrate where we have the spin motion. One is a left spin and other is the right spin. So this is what my MFM image is, right? So this magnetic force microscopy images the spatial variation of magnetic forces on sample surface, which is having the resolution of 10 to 25 nanometers. The system operates in non-contact mode. An image taken with magnetic tip contains information about the topography and magnetic properties of surface. Which effect dominates depends on the distance of the tip from the surface, because the interatomic magnetic force persists for greater tip to sample separations than the van der Waals forces. If the tip is closer to the surface in the region where standard non-contact AFM is operated, the image will be predominantly the topographic. As the separation between the tip and the sample increases, magnetic effects becomes apparent. So a magnetizer is needed to re-magnetize the tip. Note that the structure of soft magnetic samples like permalloy or garnet films or heat pump can be significantly changed in the field of the tip that has relatively high coercivity. So tip-induced reorientation of surface magnetization and surface-induced reorientation of the tip magnetization can complicate the image interpretation. So this is what the magnetically tip coated. If you zoom that particular tip, we can observe this is a magnetically coated tip. This is a part of the cantilever, and this is the first magnetic sample. This is a flat magnetic sample, right? So magnetic sample. So these are the domains. We have up domain, down domain. These are the domains, right? So when we apply some motion, when we apply some field, so these domains will try to orient in different directions. This domain will try to orient in different directions, like just like gyromagnetic. So that is what it is, having some gyromagnetic ratio. That is what the quantum mechanics frame can be explained, how the domain orientation can be simulated by using some simulation tools also. So that's what the micromagnetism or micromagnetism plays an important role in simulating this particular dynamics, right? So here we have two types of modes. This is a lift mode. One is a magnetic force microscopy, and there is a electrostatic force microscopy. So since magnetic or electrostatic force can be either attractive or repulsive, problems with feedback loop stability in the non-contact imaging mode are likely to occur. So the cantilever measures the surface topography on first main scan, and cantilever ascends to lift scan height right? A cantilever follows the stored surface topography at the lift height above the sample while responding to magnetic or electric line influences on second scan measured by different characteristic parameters like amplitude, phase, or frequency detections. So this is what the magnetic force microscopic images, right? So this is what you can see. We can see one dimension. We can see one bubble like this. So which is what we are calling it as the vortex. Which is we call it as vortex. Right? So this is a vortex. This is how it looks. That means the orientation of the spins are like this, right? So it is like vortex like, right? So there are some. If you deposit certain nanostructures on a thin films, we can observe different types of vortexes. We can observe single vortex, double vortex, and multi vortex, depending upon the topography of the nanostructure or depending upon the topography of the nanomaterial that has been fabricated on the given substrate. Right? So if you see some certain dynamics, the force executed can be given as F equals to mu naught into Q plus M dot del gradient field, right? Gradient into H. If the length of the effective domain at the tip apex is small compared to the characteristic decay length of the sample stray fields, then the tip can be approximated as a point dipole. So that is what F equals to mu naught H, mu naught into M dot H. In this case, the gradient of the stray field in the surface rather than the field itself contributes to the force signal. That is what co-tip. So that is co-tip in the sense it's a cobalt tip, right? Cobalt tip. For a large domain size, only the front part of the domain effectively interacts with the surface stray fields. So some stray fields will be exerted based on the geometry we choose. That what F equals to mu naught into QH, the field is detected, and this is generally observed for nickel iron tips. So these are certain images where we can observe the sample topography. That is what the MFM image. This is what they got in the cobalt tip, and this is what the nickel tip. So if you see here, we can see the simulated material. If you see that, see here we have certain variation observed in this case for different positions, right? So this is for the nickel tip, and this is for the cobalt tip, because these two, nickel and cobalt, are the two ferromagnetic materials. So the quantification of MFM images is virtually impossible because the magnetic state of the tip is generally unknown. The tip-induced reorientation of surface magnetization or surface-induced reorientation of the tip magnetization can be minimized by the optimal force, by some optimal forces and optimal choices of the material due to this demagnetizing fields and large magnetic anisotropy and imaging at appropriate tip surface separations. So which results in spatial resolution. An alternative approach, the other method, the alternative approach where for the application is the soft magnetic tips or super paramagnetic tips with large susceptibility. The magnetic structure of such a tip aligns parallel to the surface stray field, and the tips are sensitive to the absolute value of magnetic field. So that is what the expression is given as F equals to half chi into V delta B square. So where chi is the susceptibility and V is the effective tip volume, right? So the interpretation of MFM data from the non-homogeneous material, and current carrying devices can suffer from electrostatic contributions of from force to force or force gradient signal contact, especially for conventional metal or metal coated tips. Right. So these are the different domain structures based on the tips of iron films at different nanometer size. It is a 50 to 520 nanometers, which is 910 nanometers. And this is what we can see the block wall, and this is what the needle wall. Needle walls are generally observed for thin films, and we observe some certain case for a block wall. So this one on 110 plane, 110 plane. You see, and this is what you can see the separation between the walls. If you see, this is what the domain wall is. Domain walls. So it's for the cobalt films, and this is what for needle films, or needle walls, right? So needle films are generally for thin films. Needle walls are generally for thin films. So if you come to the electrostatic force microscopy, the silicon cantilevers are used with conductive coating. Silicon cantilevers are used with some conductive coating. The grounded tip first acquires a surface topography using the tapping mode. A voltage between the tip and the sample is applied in the second scan, that is lift mode, from 50 to 100 nanometers, to 100 nanometers to collect electrostatic data. So EFM measures electric field gradient and distribution about the sample surface. EFM is used to monitor continuity and electric field patterns on samples such as semiconductor devices and composite conductors, as well as for basic research on electric fields on the microscopic scale. So these are some of the dynamics that can be studied for studying the electro-force microscopy. It's the tip surface electrostatic forces, that is what the conductive forces. So that is what F equals to half delta V whole square into dou C Z by dou Z, where delta V is equal to the tip surface and the tip contact. So, right. So the exact functional form C of Z is complicated and can be obtained only by numerical methods such as finite element methods. So finite element method can be used to study the modeling. For finite element methods can be used to study the model of this particular static forces, electrostatic forces, tips, electrostatic forces fields, and imaging process, right? And say finite element process, and somewhere we use some different models also, right? So that is what the cantilever. So this is what some of the images that have been observed at 50 nanometers and 50 nanometers for different potentials, that is for 3 volts and 5 volts for different field materials. That is what conical field emitters, right? So this is what the force versus distance in 1 volt field applied. So this is what the distance which is taken in nanometers, and we have the force in Newton, that was measured in Newton. You see, we have these different phases. So one is based on the tip movement, and other is based on the cantilever alone, and other is the tip plus cantilever. Both 3 cases can be studied when we study about the force versus distance for 1 volt applied. So the quantification of the electrostatic tip surface interaction is significantly more complicated for dielectric materials, right? Because both the surface changes, because surface charges and volume trapped charges, as well as the tip induced polarization image charges, contribute to total force. That's why the quantification of the electrostatic force takes place. So this is what the cases we observe for the localized fields. Localized field, that is what the polarization of the charges, right? So these are some of the dynamics that can be studied. So if you see the experimental measurements can be performed with the dielectric or semiconductive or conductive tips. In the former case, the tip usually acquires a large owing to the contact electrification, the magnitude and sign of which are usually unknown. In the latter case, the electrostatic state of the tip can be controlled by external bias. For zero bias, that is grounded, tip surface charges induce image charges of the opposite sign on the probe and result in the attractive interaction, but charges on the opposite sign cannot be distinguished. For a biased tip, the force between the tip and the surface depends on tip bias, and the charges of the opposite sign can be distinguished. The feedback scheme that relies on the force gradient to maintain tip surface operation may lead to tip crash into the surface on the vicinity of the domain wall with opposite surface charges. This drawback is now avoided by using the non-contact scheme. So this is what some of the some of the dynamics that are framed to understand what is a surface scan potential microscopy, SSPM, or Kelvin probe microscopy. That is what we study about KPM, right? So these are some of the dynamics of electron force microscopy. So these are some of the images that we can be experimentally verified, right? Experimentally taken from the data of EFM. Right, so when we use a Kelvin probe microscopy, the simple interpretation of Kelvin probe microscopy in terms of surface potential is applicable only for the conductive surfaces, right? Conductive surface. Even though Kelvin probe microscopy has been successfully applied to the characterization of semiconductors and dielectric surfaces, the image formation mechanism is not clearly understood till today. So such factors as tip-induced band bending, charge injection or contact electrification and redistribution of surface absorbers all can contribute to the observed potential image, rendering its interpretation and quantification a complicated task. Nevertheless, sensitivity of Kelvin probe microscopy to the local variations of work function and Fermi level allows its application to dopant profiling in semiconductor devices. This is what we study this one. So this is what we study for different EFM images and different Kelvin probe microscopy for different materials. Right, this was taken from a Journal of Nanoscience and Technology in the year 2001. So this was the semiconductor laser, materials. Semiconductor laser, using the semiconductor laser, different potentials are being taken, right, and different capacities. So EFM is always useful failure analysis tool on the device, way for a chip level, even on the packaged integrated circuits. So this is what the topography of the film, and this is what the EFM image is, right? So the electric signal between the second and third probes on the left shows that the transistor on the left is in saturation. The topography image shows no hint for this failure. Using an emission microscopy, first the defect was detected in the vicinity of the transistor, but the cause and the exact location of the defect were not identified until the EFM image was captured. With the passivation removed, and the reactive ion each strip back to the gate oxide or atomic force microscopic topography. Images of other defective transistors are very close to the area revealed an ESD, electrostatic discharge induced rupture hole in the gate oxide of that. So this is what the case study. One case study we have seen: indium phosphorus based nanowire between two metal contacts with some bias applied. This is the topography of the film, and the Kelvin probe microscopy image is this, and this is the topography. So potential maps can be used to identify the bottlenecks to charge transport, and in conjunction with simultaneous drain current character measurements allow resistant analysis of specific structures. Example: contacts and discontinuities in the channel. So these are some of the bottom contact devices and the top contact devices. So this is what the precision control of the number and the position of the dopants, right? A semiconductor device continues to chart the normally random distribution of the individual dopants within the semiconductor becomes a critical factor in determining the device performance, homogeneity, and can no longer be assumed. So this is what we can study about the electron force microscopy. In the next lecture, we will see what is about the scanning capacitance microscopy. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.